Hi, everybody. Here is another solution as requested on the forum. Finally delivering exercise 3b from section 5.2. The question is as follows. Let V be the vector space of polynomials with coefficients from R and degree at most 2. Then let T from V to V be the linear operator defined as follows. T applied to a polynomial of degree at most 2. That will be of the form some number a times x squared plus some number b times x plus some number c. When we apply t to that, we get back another polynomial, but now the coefficients have moved around. So we get cx squared plus bx plus a, where the a, b, and the c are the coefficients that came from the original input polynomial. So the instructions are to test D for diagonalizability. And if T is diagonalizable, then find a basis beta for the vector space V so that the matrix of T with respect to that basis is a diagonal matrix. So let's begin. Let's observe that, well, we want to be working with matrices. That's usually the best way to identify eigenvalues and find eigenvectors and so forth. So let's choose a basis for V to begin with. So I'll call it alpha maybe, since beta is going to be the basis of eigenvectors, if we can find such a thing. So I'll use a different letter alpha to be a nice basis for this vector space V. I'll use the standard basis on P2. So that'll be 1, and then x, and then x squared. Right, there's a reasonable, nice standard basis for polynomials of degree at most 2 over the real numbers. So with respect to this basis, we should be able to write down the matrix for T. Well, it's going to be a 3 by 3 matrix. To get the first column, we should apply T to the first vector in that basis. That's 1. So T of 1, that would be A equals 0, B equals 0, and C equals 1. So that should output the polynomial 1 times x squared plus 0 plus 0. So 1x squared, written in terms of this basis alpha, well, that would be 0 1's and 0 x's and 1x squared. All right, next, we would turn to the second vector in this basis. The vector is x. So when we apply t to x, that's really the polynomial 0x squared plus 1x plus c. So the output will be just 1x, which means that the polynomial written as a linear combination of these guys would be 0 times the first vector, 1 times the second vector, 0 times the last vector. And finally, when we apply t to the third vector, x squared, that would be when a is 1, b is 0, and c is 0. So then the output would be just 1. Well, 1 is clearly 1 times the first vector plus 0 times the second vector, 0 times the third vector. So the coefficients would be 1, then 0, then 0. Great. So now we have a matrix for T with respect to some bases. This is clearly not a diagonal matrix, although it's some sort of anti-diagonal matrix, but that's not really the thing that we're looking for. So instead, what we're going to want to do is find the eigenvalues for this. So let's give this a new name so I don't have to write the brackets all the time. Let's call that matrix A, just for convenience, capital A. Then we can write down the characteristic polynomial for A and for this linear transformation by calculating the determinant of A minus T times the identity. In this case, that will be the 3 by 3 identity. So let's see. A minus T times the identity, that's going to be this matrix, but we're going to change the diagonals by subtracting T from each. So we're going to get 0 minus T is just minus T. We're going to get 1 minus T in the middle, and then another minus T in the bottom right, and then all the other entries will stay the same. So that should be a 0, that should be a 1, there's a 0 and a 0, that's a 1, and that's a 0. Right, so that's the A minus T times the identity matrix. And now we want to compute the determinant of this matrix. Well, let's see. I guess if we went, say, along the second column or the second row, then we'd have a number of zeros. So that's pretty cool. Let's do that. That'll be probably the easiest way to proceed. So let's see. 0 would be -1 times 0 times the resulting subdeterminant determinant. So then I would have 1 minus t times the determinant of the resulting submatrix. That should be minus t times minus t is t squared, minus 1 times 1, that's t squared minus 1, and then plus 0. So that's great. That'll give us a nice factored form, almost factored form. T squared minus 1 factors nicely, and then 1 minus t is already a linear factor. So that's a great, easy way to do that. But let's just stop for a moment. Let's suppose that we hadn't recognized that doing this determinant along the second column would be so nice. Let's just suppose we tried to use the first column instead. That would be a minus t times the determinant of the resulting submatrix. That would be 1 minus t times minus t minus 0. Right? And then if I go along the first row, that would be minus 0. And then it would be plus 1 times the determinant of the resulting submatrix, which would be 0 minus 1 times 1 minus t, minus sign there. And well, then we'd be in a slightly tougher spot because this doesn't look like it factors nicely. At least it's not in a factored form. So we'd have to do some work still. So let's do some work. Let's simplify this, write it out as one nicer, standard polynomial form, which means we're gonna have to multiply some stuff out. So we're gonna get a minus t times 1 minus t times minus t. That should be a minus t plus t squared. And then 1 times 0 is 0. 1 times minus 1 is minus 1. So I guess we would get a plus t and a minus 1 if we sort of use that minus sign nicely. And then we'd still have to distribute this first t or minus t in front. So then we get a t squared minus t cubed plus t minus 1. And probably this would be best written in descending order. Minus t cubed plus t squared plus t minus 1. All right, so then at least we'd have a polynomial in a nice polynomial form, but it's still not clear what the factors here are. And it's not a quadratic, so there's not really always an obvious way to figure out how to factor such a thing. So I guess what we would do is just try some stuff. Let's see if we can figure out one of the roots of this polynomial. Let's try t equals 0. That's 0, 0, 0, minus 1. Nope, that's not 0. Okay, let's try, I don't know, 1. What happens if we plugged in 1? Well, then we'd get minus 1 plus 1 plus 1 minus 1, which would be 0. Great, so just sort of by trial and error, we can see that 1 is supposed to be a root of that polynomial. Whoops. Which means that this polynomial should be able to be written as either t minus 1 or 1 minus t. I think I'll write it as t minus 1 times something. Let's figure out what that something would be. Well, we'd have to do, for instance, polynomial long division. What happens if we divide minus t cubed plus t squared plus t minus 1 by t minus 1? Well, to get the first terms matching, I would need a minus t squared. So it would give us a minus t cubed plus t squared. And then when we subtract, we get 0. Well, then we'd bring down the plus t and the minus 1. Oh, and then I guess it's pretty clear that if I just added 1 here, I'd get t minus 1, and then when I subtracted that, I had 0. So it is the case that this polynomial times that polynomial equals this cubic polynomial we started with. So t minus 1 times minus t squared plus 1 is equal to the polynomial we started with. And then that's a difference of squares. So we get the same factored form that we had when we tried to calculate this determinant along a different column. We get a t minus 1, and then I guess a 1 minus t, and then a 1 plus t. And just for good measure, let's write this all in the same form. This will be minus 1 times 1 t minus 1 squared, and then t plus 1. All right, so we get the same polynomial either way, but just I wanted to do a quick exercise to sort of recognize that whether we get from this determinant a polynomial that's already factored or not, the question of whether or not the polynomial splits is it's well defined, even if it's not always easy to answer. So let's observe that yes, this polynomial does split. All the roots of the polynomial are shown in the linear factors, and each, this is written as a t minus 1 and t plus 1. Well, those are definitely real numbers, 1 and minus 1. So this is fine. It splits over the field R. So good. T splits. That doesn't mean that T is in, I shouldn't say T splits, I'm sorry. I should say that the characteristic polynomial for T splits. The characteristic polynomial for T splits. Now that doesn't mean necessarily that T is diagonalizable. It just means that T isn't obviously not diagonalizable. If T didn't split, if the polynomial didn't split, then we would know instantly that T was non-diagonalizable. But since the characteristic polynomial does split, there's a chance that T is diagonalizable. So let's observe now. We know what our eigenvalues are. I'll call lambda 1 is, I'll call that one 1. And it has algebraic multiplicity 2 because of that power of 2 on the factor t minus 1. And then the second eigenvalue is negative 1, and it has algebraic multiplicity 1 because the power on that t plus 1 factor is just 1, secretly 1. We don't usually write that power. Yay? All right, so in order to determine whether or not T is diagonalizable, we would have to determine whether the eigenspace according to, or corresponding to lambda 1 is 2. And, well, the eigenspace can't be any larger than 1 and their dimension 1, and there must be at least one eigenvector corresponding to the eigenvalue negative 1. So there's nothing to check there. We actually already know that the dimension of the eigenspace corresponding to the eigenvalue negative 1 does match the algebraic multiplicity. It'll be 1. All right, but we're going to work with that eigenspace anyway because we want to actually find the basis if we do eventually find that T is diagonalizable. We're going to find a basis of eigenvectors. So either way, let's proceed. Let's look at, let's start with the eigenspace E1. The eigenspace corresponding to the eigenvalue 1. Well, that means that we should be looking at the null space of A minus just 1 times the identity. That's just the identity. So that means that we're looking for the null space of the matrix A minus the identity. So that'll put a minus 1 in the top left corner and a 0 in the middle and a minus 1 in the bottom right corner. And then everything else should stay the same. We'll have a 0 and a 1, a 0 and a 0 and a 1 and a 0. Yay. All right, well, we know that the null space is unchanged by elementary row operations. So very conveniently, we could probably just add the first row to the last row and immediately get 2 rows worth of zeros. And now we can see pretty quickly that this null space should have 2 free variables. In fact, the resulting system of equations, if we called our variables x, y, and z, for instance, what we would know is that our solutions would have to have the form minus x plus z equals 0. So z could be whatever it wanted to be, y could be whatever it wanted to be, and x would only be constrained in terms of z. So in particular then, I guess we could write this entire null space as the span of, actually, before I write it as a span, let me write it this way. This should be the set of all vectors of the form, as we said, z could be whatever we want it to be, so maybe I'll call it t as a free variable. Y could be whatever we want it to be, so I'll call it s as a free variable. And then minus x plus z would be 0, so x would have to equal z, so I guess that first component would have to be the same as whatever that last component was, where s and t are allowed to roam freely among the real numbers. And now we could write down a basis for this space pretty nicely. For instance, if we let s be 1 and t be 0, then we'd get the vector 0, 1, 0. And if instead we let t be 1 and s be 0, we'd get the vector 1, 0, 1. And a quick check to see whether or not these are in fact eigenvectors of that matrix reveals quickly that yes, in fact, they are eigenvectors with eigenvalue 1. So great, that means that we have a 2-element basis for this eigenspace, and the algebraic multiplicity of this eigenvalue was 2. So we know, yes, the dimension of E1 equals the multiplicity of the eigenvalue 1. Well, that tells us already really that the linear transformation should be diagonalizable, but let's just check the other eigenspace anyway, since we're going to have to no matter what. So the other eigenvalue is -1. So the eigenspace corresponding to that eigenvalue, that should be looking for the null space of A minus -1 times the identity. Well, that's just A plus the identity. So that's the null space of this matrix. But we're going to add 1s along the diagonal. So that will give us a 1 and then a 2 and then a 1. Everything else in the matrix stays the same. So now we're looking for the null space of the matrix 1, 0, 1, 0, 2, 0, 1, 0, 1. Again, we can do some elementary row operations without changing the null space. So I'll leave the first row the same. The last row could be eliminated really easily by subtracting or adding negative the first row to the third row. And I guess we could multiply the second row by half and get 0, 1, 0 fairly quickly. So this tells us that we should have 1 free variable. So if we were to write the vectors in this null space, I guess y, the middle component, would have to be 0, coming from the second row's condition. And we could write down the last component as a free variable. Maybe I'll call that t. And then the equation x plus z equals 0 would mean that the first component has to be the opposite of the third component. So that would be a minus t, again, where t is now allowed to roam through all the real numbers freely. So a nice basis for this null space could be the set containing the one vector -1, 0, 1, obtained by letting t be 1. Right. There are lots of choices here. You let t be anything you'd like, but sort of choosing t equals 1 is a nice, simple way to write that down. And right, again, we could check pretty easily that if you multiplied the vector -1, 0, 1 by this matrix A, you would get the vector 1, 0, -1. In other words, the eigenvalue -1 times that vector. Great. This is almost what we want now. We know that, let me write the last step down. Yes, the dimension of the eigenspace corresponding to eigenvalue -1 equals the multiplicity of lambda 2, which was -1. So now we've really directly verified all the conditions of the main theorem from this section, namely that the characteristic polynomial of t splits and the dimensions of the eigenspaces match the multiplicity of the corresponding eigenvalues. So we can conclude definitively now t is diagonalizable. Huzzah! This means that we can do the last step. If it is diagonalizable, we can find a basis beta for V so that the matrix of T with respect to that basis is a diagonal matrix. The only problem is that the vectors that we found that we want to use to build a basis, well, those are bases for R3, not for our original vector space, a space of polynomials. So finally, what we should do is translate our coefficient vectors back into vectors in V. So 0, 1, 0, 1, 0, 1, and -1, 0, 1. Well, those are just the coefficients representing vectors from this basis alpha. So the vector 0, 1, 0 means 0 times 1 plus 1 times x plus 0 times x squared. So the corresponding vector in V is just x. Similarly, this 1, 0, 1 means 1 times 1 plus 0 times x plus 1 times x squared. So this should correspond to the vector 1 plus x squared. And finally, this last coefficient vector, -1, 0, 1, that should correspond to -1 times 1 plus 0 times x plus 1 times x squared, which I could write as -1 plus x squared, or maybe it looks better as x squared minus 1. But in any case, we now have a basis beta for V. It's the set containing the three vectors in our vector space of polynomials. The first is x, the second is 1 plus x squared, the last is -1 plus x squared. Right? The only thing we could maybe do now is check that this is right, that in fact the matrix for T with respect to this basis is a diagonal matrix. So let's just go ahead and do that. Let's apply T to the first vector in beta, that would be x, and remember what T does. T takes a vector like this and sort of changes around the coefficients. So x would just have a equals 0, b equals 1, c equals 0. So that should return the vector x. And written as a linear combination of these vectors in beta in this order, this would be 1 times x plus 0 times 1 plus x squared plus 0 times the third vector -1 plus x squared. So the first column of the matrix for T with respect to beta would be 1, 0, 0. Great. Now let's apply T to the second vector, 1 plus x squared. 1 plus x squared should have C as 1 and A as 1. So then it would, T would return the vector again, 1 plus x squared, which, well, in respect to the standard basis, that would be like 1, 0, 1. But with respect to this basis beta, we can see that that is just the second vector in the list. So it's actually going to be 0 times the first vector x plus 1 times this middle vector 1 plus x squared, and then 0 times the last vector minus 1 plus x squared. So the second column of our matrix should be 0, 1, 0. And finally, if we apply t to the last vector in our basis, negative 1 plus x squared, we're going to get, well, let's look back at t. That means that c is equal to minus 1 and a is equal to 1. So I guess we're going to end up with a minus 1, that's our c, times x squared plus 1. That's our a. And now, well, that looks an awful lot like that third vector in beta, except differing by a minus sign. So written as a linear combination of the vectors x and 1 plus x squared and minus 1 plus x squared, we should have coefficients 0, 0, and minus 1. So then that tells us that the third column of our matrix should be 0, 0, minus 1. So let's go ahead and write this down now. T with respect to our chosen basis beta should be, we said 1, 0, 0 as the first column, 0, 1, 0 as the second column, and 0, 0, minus 1 as the third column. Notice not only is that a diagonal matrix now, but the values in the diagonal entries are the eigenvalues, and they come in the corresponding order that we wrote the basis vectors beta in. The eigenvalue of x was 1, so 1 is the first diagonal entry. The eigenvalue of that vector was also 1, so 1 is in the second entry of the diagonal. And the eigenvalue of this vector was minus 1, which is why we have minus 1 in the third entry. If we were to change the order of these vectors in beta, it would change the order of the diagonal entries in this matrix, because a different ordered basis will give you a different matrix with respect to that ordered basis. But nonetheless, we would still have a diagonal matrix because the vectors are eigenvectors, and the order of the eigenvectors should determine the order of the eigenvalues in the diagonal matrix. Hopefully that is a helpful and conclusive example to sort of demonstrate really what is going on in this section, and I am happy to answer any other questions. If you have any, please post in the forum. Have a great weekend, and I will see you guys next week at the final.